And we have about 10% international students. We are working, I think, similar to what's going on here in Hiroshima on, being more international and more supportive in order to increase that fraction of international students and also, of course, postdocs and faculty members. If you just compare this, to Hiroshima University, at least the numbers I found on Wikipedia say that Tel Aviv and Hiroshima have about the same number of faculty members, but there's about a factor of 2 in the number of students, which means that students here get, I assume, a much better guidance from professors compared to what we have in Israel. Well, again, another HU that Ivan mentioned on Monday, which is Harvard University, there actually the numbers are pretty similar to Hiroshima in terms of this student to faculty ratio, which I think is great. One big difference between Tel Aviv and Hiroshima, are temperatures. So I was walking around with a t-shirt and barefoot and swimming in the sea last week. You can see here the minimum and maximal temperatures. And again, I think one of the important things here is also the water temperature in the sea, where, even in the winter, you can go in without the wetsuit and swim, which is really great. And again, we're also walking distance from the beach, as Ivan can tell you. So I'm a faculty member in the School of Mechanical Engineering, but I'm also affiliated with several organizations on campus. One of them is the Center for Physics and Chemistry of Living Systems in Tel Aviv, which connects together 30 faculty members from many different departments, all researching all kinds of different aspects of biological and soft matter physics and chemistry and some engineering. This center isn't, well, maybe it's big in terms of number of faculty members, but it's not huge in terms of money and administration, etc. It's mainly of a community of people that are on the same campus doing related things. We have seminars. Another thing that has started recently is discussions or informal seminars that faculty members are not allowed to attend. It's only for graduate students and postdocs, and I haven't been there, but I've heard that it's going very well. And again, all this is leading not only to collaborations and joint publications, etc., but I think more importantly to just building a scientific community. So this is the Center for Physics and Chemistry of Living Systems. Some of us are doing things that are really biophysics. Others are doing things that are, maybe just adjacent to looking at biological systems, or for instance, part of my research is related a bit to biological systems, but then most of it is what we call dead soft matter systems. But still, we are together under the same roof. Another center that I'm involved in is the Sackler Center for Computational Molecular and Material Science. And this is a slightly smaller group of faculty members that are all doing essentially computational research in different domains. And the main thing actually that this center encompasses is that we have a postdoc fellowship program. And actually this month we are evaluating applications for next year's fellowship. So if you know of anyone that would like to come to Tel Aviv for a postdoc, and obviously we can somehow, if it would be with me, we can of course combine it with some collaboration with people here. Then please let them know. And finally, I'm very happy to be part of this SKCM² initiative, and it's really great to be here. And I'll use this opportunity to, I think, personally thank Ivan and Manabu for inviting me to join, and all the staff here for being really great and supportive and arranging everything so smooth. So back to my talk, I wanted to tell you today about mechanical metamaterials and specifically combinatorial metamaterials. In the moment, I'll try to explain what do I mean by these words and where these images came from. A key feature that you will see will repeat in many of the issues that we are dealing with in mechanical metamaterials is frustration. So I'll start with a few words about frustration. Oh, sorry, before that, so I won't forget this. I'll thank all my students and collaborators here. So the top row are students and postdocs that have been working with me on this topic along the years. My group isn't that huge. At the moment, only the last 5 are active. The first 4 already moved on. And all this is in very close collaborations with one experimental group, or actually by now it's split into 2 in the Netherlands, and another experimental group in Tel Aviv, and also theoretical collaboration with a colleague in the US. But anyway, I want to start with a few words about frustration. So, at least when condensed matter physicists think of frustration, they think of antiferromagnetic Ising models. So let's say you have a square lattice and you have these particles that, you can think of them as electric charges or magnetic moments, but you can just simply think of them just as red and blue balls. And let's say there's an antiferromagnetic interaction between every nearest neighborhood pair such that they want to be opposite colors on the square lattice. You can easily satisfy that. Now, if you have what's called a spin glass, where you have some random interactions that some of them are ferromagnetic, these black bonds, and some of them, antiferromagnetic, these black bonds, but others are ferromagnetic, these orange bonds, where you have a pair that wants to be the same. Now, when you go around the loop in this lattice, some of the loops are fine. You can find a solution for these blue and red balls such that everyone's happy, but some of the loops, like this one here, is frustrated. There is no way to simultaneously satisfy both of these bonds. Okay, something related or similar happens when you have some incompatibility between the symmetry of the lattice and the symmetry of your degrees of freedom. So you don't necessarily need to have disorder as in spin glass. You can also have what's called geometric frustration coming from geometry. For instance, the most famous one is the antiferromagnetic Ising model on the triangular lattice. And this frustration causes such systems to remain disordered no matter how much you cool the temperature. The ground state is disordered. It's degenerate. It contains many different configurations that all are equivalent energetic. Actually, Ogawa suggested that you can realize this antiferromagnetic Ising model on the triangular lattice by confining hard spheres between 2 parallel walls. Why is that? Because if you confine spheres to a monolayer, you can think of this as if you just have a packing of disks in the plane. And as you increase the density, the best way to pack disks in the plane is this hexagonal packing shown here, okay, which looks just like our triangular lattice we started from. But now, if you separate the walls, or you make sure that the separation between the walls is slightly larger than the particle diameter, these particles have some freedom to move out of the plane. And that freedom causes every pair of spheres to want to be as far apart as possible, because then you maximize their entropy or free volume. And the way to keep a maximal distance is to use that motion out of the plane in order for this monolayer to buckle, such that you'll have one sphere close to the top plate, the other sphere close to the bottom plate, and there would be a preference for neighboring or an effective interaction causing neighboring spheres to want to be in opposite states. So this is exactly like those red and blue dots I showed you before that want to be in opposite states at adjacent sides of this lattice. So naively, you would say that this soft matter realization maps to the anti-fermatizing model on the triangular lattice, which is well known to be disordered. So my colleague Ilan Khan, who was then a postdoc at Penn, at the same time as I was there, realized this experiment. And here you can see micron-sized spheres. And some of them appear bright, some of them appear dark, just because they are at two different heights. So that's the white ones are in focus, the dark ones are just out of focus. They're a bit further away in this microscopy image. I'm sorry, there's no scale bar here. And you can see these stripes. So instead of getting the disordered configuration that you would expect in this simple Ising model, Elon observed stripes, and we then started this theoretical research in order to explain where these stripes come from. And the story is all about geometry and packing. So I tried to convince you before that if you have spheres in a single layer, the best way to pack them is in a hexagonal packing. If you have some ability to move out of the plane, packing considerations tell you that you can come closer together if you buckle out of the plane. But now, when you consider such a triplet, which would be our minimal loop in the lattice of spheres that are in contact, every pair of contacting spheres which are in opposite heights come closer together, and therefore the projection of their distance onto the horizontal plane is shorter than the distance between them if they're at the same height. So this means that if you take a top view of this tilted triangular lattice, this tilted equilateral triangle, you get an isosceles triangle like shown here. Okay, so you can now consider all the possible local configurations of a single sphere and its 6 neighbors. So again, I'm marking here black and white for up and down. So again, up to rotations and inversions, there are only these 5 configurations. And actually, Ogawa in his original paper also studied the statistics of these different configurations. Now you can ask yourself, when you have this deformation of the lattice because of that tilting and changing to isosceles triangles, can you tile the plane with the isosceles triangles according to these different configurations? And it turns out that you cannot do it for all of them. There are only these 2 configurations where the triangles perfectly fit, and in the different cases, the angles don't sum up to 2 pi. Therefore, you would expect in this hard sphere problem to get configurations like this. And this is just a motif of a straight stripe, and this is a motif of a bend in the stripes. And this is the very simple geometric explanation for why we see stripes experimentally. Again, if you have a configuration which is a perfectly possible ground state configuration in this naive Ising model, you map it to this triangular tiling, you get lots of white space, whereas if you have some zigzagging stripes configuration like the one shown here, you get perfect tiling. And again, I won't get into these further details. But anyway, now back to mechanical metamaterials, and I'll try to show you where geometric frustration enters also there, again, at least in the things that I'm doing in that context. So I'll start by maybe introducing mechanical metamaterials, combinatorial metamaterials, just by a specific example. So think again of that beloved triangular lattice, and now we're going to go to even larger length scales. So now, if again, originally, people in magnetism thought of lattices of atoms and molecules, and then I showed you our work of lattices of micron-sized colloidal particles. Now I'm going to build a lattice out of these centimeter scale toys. Okay, so now I have a big triangular lattice. Every triangular plaquette in that lattice is going to be made out of these toys. Again, I'm sorry, there's no scale bar here, but soon you'll also see fingers. So this is on the scale of centimeters. So all these are just rigid bars, and these are just magnets so that you can rotate your connection around each one of them freely. And the reason to consider this specific unit cell is that you can deform it without changing the length of any one of these bonds. Okay, so we think of this as a zero energy mode, or in mechanics, it's also called a floppy mode. It's a mode in which you can change the configuration without any energetic cost, without any resistance. And in this case, it would geometrically, this means just without changing the length of any of the bonds, right? Because if you have such a plastic bar and you want to bring its two ends closer together, there's obviously that you need to invest some, apply some force or invest some energy. So now we're going to take this unit cell that hopefully everyone realizes that it is anisotropic, and we can now put in each unit cell in the lattice, put this exact same unit cell, but put it in a different orientation. So I can now take a periodic triangular lattice and now position in each site of that lattice that same unit cell, but in a different orientation. So I get a non-periodic structure, and there's a huge set of possible such metamaterials that I can realize by orienting them in different directions. And now, one question you can ask is, if your unit cell is floppy, has this zero energy mode, does this entire structure or metamaterial have a floppy mode? Okay, so that seems like a very non-trivial question. In order to answer that, we're going to, maybe in the spirit of what I showed you before, we're going to start from some local loop in this lattice. So now a local loop would be just such a super hexagon made out of 6 super triangles. So I'm going to compare these two loops, okay, and try to see whether I can simultaneously deform each one of the triangles in this hexagon according to that floppy mode I showed you before. And it turns out that this configuration here on the left, you can do that. You can simultaneously deform each one of the triangles to one of those two states I showed you before. And again, I'm not showing you the actual displacement. I'm just marking these yellow arrows for the direction of the displacement. And you can verify that here everyone's happy, and you can do that. Whereas in this configuration here on the right, you cannot do that. If you start from a certain triangle and propagate that information, you'll reach a contradiction somewhere. So we would say that this is frustrated. And now experimentally, and here on the fingers, you can see that the structure on the left deforms without changing the length of any of the bonds. So all the deformations here is just by changing the angles, whereas this structure here on the right, you can see that some of these yellow bars bend, and they now look like these bananas, which means that the end-to-end distance became shorter. Okay, so again, I didn't bring these samples today with me, so you cannot feel that this is softer and this is stiffer, but you can see just by the image, you can see that here you have deformations that are also bending of the beams and not only changing the angles at the corners. But let's try to understand what is the reason that this structure here on the left is what we call compatible or floppy, and this one here on the right is frustrated. The reason for that is that you can, again, similarly to what I showed you before, you can now just label the nodes where we had that displacement vectors in the yellow arrows a second ago. You can just label them by alternating red and blue dots for the two possible directions of the displacement. And then for this compatible configuration on the left, as you go around the loop, you have an even number of such red and blue dots, and therefore you can return to what you started from. Whereas for the configuration here on the right, the perimeter of the loop is odd, and therefore you cannot assign alternating red and blue dots without any conflict. Okay, so the key for compatibility or having a global floppy mode is that all these minimal loops would have an even perimeter. So now let's try to characterize and identify all the possible compatible structures. So the way to do that is to look at all these positions where these displacement vectors are defined. Okay, so these are on the centers of the edges of this black triangular lattice. And now at each such point, I have two possible directions of the displacement. So we'll label them by, let's call this spin plus and spin minus, spin up or spin down. Again, no physical meaning. It's just a binary variable sigma, which is plus or minus 1. And now my condition is that I do not want to have configurations like the ones shown here, in which all three edges move in or all three edges move out. And you can verify that in these configurations, the sum of these spins is plus or minus 3. Whereas a desired configuration would be a configuration in which in each triangle I have 2 in and 1 out, or 2 out and 1 in, and then the sum of these three variables is going to be plus or minus 1. So I can now define a Hamiltonian or some penalty function that would just be the sum over all such triangles, these purple triangles in the Kagome lattice, of sigma 1 plus sigma 2 plus sigma 3, the sum of these three binary variables squared. And I now want to minimize this object in order to avoid these plus minus 3s. I want everyone to be plus or minus 1. Okay, so I'm going to try and minimize that energy function or Hamiltonian or penalty function. You can call it however you want. And then, okay, this is just one, even half a line of algebra to open this square and map this free body interaction into a two body interaction. And this model has been studied coincidentally also by people here in Japan, and who have shown that if you consider the Kagome lattice with anti-ferromagnetic interactions between nearest neighbor bonds and search for the ground state of that model, that ground state, similarly to the triangular lattice that one year studied and I mentioned before, is disordered. Okay, because of this frustration, because frustration in it, different story. It is disordered, which means that there are many, many possible configurations of these spins on the Kagome lattice that would satisfy these conditions. Okay, and the degeneracy, the number of such configurations grows exponentially with system size. Okay, so now let's see how we can take one of these many, many configurations and generate a metamaterial out of it. So now I'm going to consider a specific ground state of this Ising model on the Kagome lattice. So these are these red and blue dots, and I've assigned them such that in every purple triangle, I have exactly 2 blues and a red, or 2 reds and a blue. I never have 3 blues or 3 reds. Okay? And now, for a moment, I'm going to forget about this, the underlying triangular frame. I have just this Kagome lattice. And now, in each triangle, in the metamaterial, I have only 2 out of the 3 bonds. So I can just erase the bond between the 2 ferromagnetic points. Okay, and then I get such a network or a graph, if you want, which is bipartite. All the loops here have, an even perimeter. And again, if I'll show back this triangular reference, I have a metamaterial which seems to be disordered, but actually it's not disordered. It is non-periodic, but it's not random, because I generated it in a very specific way that would assure that it would be mechanically compatible. And then my colleagues 3D printed these structures. And this is, again, it's a structure that apparently seems to be disordered, but it was designed from a ground state of the Kagome lattice that would assure that you can deform this only by changing angles without changing the length of any of the bonds. Okay, and the reason behind it, again, is parity. It's just that the perimeter of such loop has to be even. This allows us to introduce defects or imperfections into these metamaterials. So I'm going to start from a compatible metamaterial that I constructed like I've just shown. Every single loop in it has an even perimeter. Therefore, also, if you have some big loop going around the entire system, it would also have an even perimeter. I can now take one triangle and just rotate it. When I rotate it, I create a dipole, okay, a pair of 2 loops. One of them its perimeter increased by 1, the perimeter decreased by 1. Therefore, I have two odd loops here. However, in the far field, if I look far away from this, far enough from this defect, I do not sense the presence of that defect, because far away, all the loops have an even perimeter. But I can now take this dipole and separate it into two monopoles. And because the system is finite, I can pull one of the monopoles to the boundary of the system. The boundary of the system, all the loops are open, and therefore that information is erased. So I can stay with one odd loop here in the middle. All the other minimal loops in the lattice around it are even. Therefore, if I calculate some winding number or something related to a Burger's vector, just look in the far field around this defect, I would sense its presence. I would have an odd perimeter, even if any big loop going around it. Therefore, there is some topological charge to this defect. Okay, so even if I remove the core of that defect, and in a moment I'll show you how we really cut out a certain region of the metamaterial, in the far field you do feel that there was a defect in there. So just a quick demonstration of the non-trivial and long-range mechanical consequences of having such a topological defect. And here we've created such mechanical metamaterials and cut out the central region. We can create such a metamaterial without a defect in the middle, or we can create a metamaterial with a defect in the middle, and we just cut out the core around the defect in order to not get into problems. Now, if the metamaterial is topologically trivial, this means that any loop in the lattice would have an even perimeter. Therefore, if I consider 2 points here and here, the distance between them above the central cut region and below it must be either both even or both odd, right? Such that the sum would be even. If I have a topologically non-trivial metamaterial with a defect in the middle, the total perimeter is odd, which means that on one side I would need to have something odd, and on the other side something even, but I don't know whether the odd is on the top or on the bottom. Okay. So now what I'm showing you here, these two images are the exact same metamaterial, but I'm now considering lines between slightly different triangles. Okay, so you can see that this triangle here is slightly different than the triangle highlighted here. Similarly, here on the right, this is the exact same topologically non-trivial metamaterial, and I'm showing you the lines between slightly different triangles. So this triangle here on the right is slightly different than this triangle here on the right. Okay, so now what we're going to do experimentally is to simultaneously pinch two triangles. Okay, so these two triangles that are highlighted in yellow here on the left and on the right of my ring, I'm going to simultaneously pinch them and see how does the system mechanically react to that. If my system is topologically trivial, there are two options. Either the distance between these two triangles that I'm pinching is even, and it's even both above and below, then I'll just excite the global floppy mode in the system. So all the nodes would move, all at the same amplitude, the length of none of the bonds would change, and I'll get something that looks like that. I'm drawing here just arrows for the motion of the different nodes in this network. However, if the two triangles that I'm pinching are separated by an even length, and it has to be even both above and below this central cut region, then I will have some incompatibility both along the top band and along the bottom band, and that would cause some stress to concentrate both along the top band and along the bottom band. Okay, I just have changes in the length of the the different bonds both above and below, and I'm plotting here in color the deformation of each one of the bonds. Okay, and it's the same scale also here. Just here that energy is zero, so all the bonds are white here. If I have a topologically non-trivial structure, I must have one path which is even and the other path which is odd. Along the even path, I have mainly displacements without any stress, and along the odd path, I have lots of stress. And now by a very small change of whether I pinch this triangle or this triangle, I can flip the roles of the top and bottom. I can decide whether the stress would go from, go around the defect from the left or from the right, and you can see this dramatic difference between these two configurations. Okay, these are results of a very, very simple mechanical model, which just assumes that this network is made out of just a network of masses connected by springs. If you now look at an actual experiment from some 3D printed mechanical metamaterial, you see essentially the same phenomena. Here, mainly displacement, here mainly stress, both above and below. Here, stress mainly above, and here stress mainly below. But you can clearly see that the experiments don't look exactly like that simple theory. The reason for that is that experimentally, we don't have perfect hinges here. It's just that the material becomes thinner such that it's easier to bend there. But still, there is some resistance to changing angles. If we add to our theoretical model also some rigidity at these hinges, we get really quantitative agreement with also further details to the experiment. So that was a bit about combinatorial metamaterials, how to make them mechanically compatible, how to introduce defect, and how to get long-range mechanical responses due to topological defects. Let's now look at this additional mechanical metamaterial. I can now construct all kinds of metamaterials made out of these macroscopic building blocks and different lattices. Now I want to show you some things about the honeycomb lattice. So I'm going to take this hexagonal building block. You can verify that, or believe me, that it is designed such that it would have a floppy mode that looks like this. So along the horizontal axis, you would either go in or go out. If you go in on both sides in the horizontal axis, then the other directions go out. If you go out along the horizontal axis, you go in along the other directions. And now, if you forget for the moment about the internal structure of this unit cell and just think about its mechanical functionality, think only at these yellow arrows. I can draw a symmetry axis here in the vertical direction, because in terms of the displacements, there's this left-right symmetry. So I can now take my honeycomb lattice and orient each repeating building block in one out of 3 possible orientations, and I'm going to denote these 3 possible orientations by these red lines. And this immediately looks like some nematic field in 2 dimensions. And that nematic will return in a moment. I now want to understand the mechanical compatibility or frustration in this system. And as before, in order to test whether there's frustration or not, I need to look at a loop. I need to start from one place, propagate my information about the state of the system as I go in the lattice to other building blocks until I return to where I started. And then I want to see whether I'm consistent with what I started from or not. The minimal loop in the honeycomb lattice is just 3 hexagons surrounding one point in the lattice, and up to rotations and inversions, there are only 4 possible ways to orient these 3 hexagons, which are shown here. And you can verify that for these 2 configurations shown on the left, you can simultaneously deform each one of the 3 hexagons according to these simple rules, whereas for these 2 configurations here on the right, there's frustration or there's conflict. You cannot do that simultaneously. Okay. Therefore, we're going to say that these situations in which a red line terminates or a red line branches are mechanical defects in our structure, and these look exactly like topological defects in a nematic directive. Okay. But now I think that this analogy to liquid crystals is very useful. But in order to generalize things even more, we realize that we need a slightly different formalism. So let's look again at why these configurations are frustrated and these two configurations here on the left are compatible. I now want to look at the direction of the displacement of each one of these edges. So this displacement here is rotating in the counterclockwise direction around this vertex. This displacement here is also rotating in the counterclockwise direction around this vertex. Therefore, I say that if I move from this edge to this edge, the sense of orientation around their common vertex here is preserved. So I want to think of this as something similar to a ferromagnetic interaction. Okay, so I have these binary variables of whether I'm rotating in the counterclockwise direction or in the clockwise direction, and then I'm going to move between adjacent points where these displacements are defined and check whether I stay with the same sense of orientation or whether I flip it. So you can see that going from here to here, I'm rotating in the same direction around their common vertex. Going from here to here, I'm rotating clockwise around the same, around their joint vertex, and therefore this interaction, I would also call it ferromagnetic. Whereas if I go from here to here, with respect to their common vertex, I'm flipping from being counterclockwise to being clockwise. So I'll say that there is an anti-ferromagnetic interaction between these two states. Okay. So now let's try to draw these ferromagnetic and anti-ferromagnetic interactions in these loops when I now bring three hexagons together. It turns out that for these two compatible configurations shown here on the left, you have either 0 or 2 anti-ferromagnetic interactions. So the number of anti-ferromagnetic interactions in the loop is even. Whereas for these two configurations here on the right, you have either 3 or 1 anti-ferromagnetic interaction in this small triangular loop here in the middle. This is the reason that we have a mechanical incompatibility or frustration in these two configurations here on the right. We can now do all this also in 3D. And actually a historical remark or chronological remark, we started all this investigation in 3D. And we managed to understand a lot of things, but we realized that it's too hard for us to proceed there. And then we went down to 2D, understood all the things that I just showed you, and then we, using that understanding, we went back to 3D and managed to do a bit more. And I'll demonstrate this in a moment. But I think that for the presentation now, it's maybe easier to going up from 2D to 3D rather than just chronologically according to our work. Anyway, I now want to do the same thing in 3D. So I'm going to take a simple cubic lattice made out of these building blocks. Why these building blocks? Because this direction, which we'll call the Z direction, the faces in the X and Y directions move outwards, as you can see here. But if you now take this building block and press on it from the X direction, the Z direction goes up, but the Y direction goes in, as you can see here. Okay, so now I have a simple cubic lattice. On every face of that simple cubic lattice, I'm going to have some displacement vector telling me whether that face is going in or out. And I can orient each such building block in one of three possible orientations and consider some complex combinatorial metamaterial in which I have many possible ways to orient these building blocks in my lattice. And I'm going to ask what are the mechanical properties of such a non-periodic structure. Okay, and you'll see that again the same notions and ideas that I've demonstrated so far will be used also here. Okay, so the first thing is to check frustration versus compatibility by going around the minimal loop. And maybe before that, I'll just show, sorry, that's going to be the next slide. Before that, I'll just show you what happens in the ordered periodic configuration. So now instead of that complex structure I showed you before, I can orient all the building blocks in the same direction, let's say in the green direction. So it looks like that. and when it is pressed, you can see alternating in and out displacements here. Okay, so we're seeing only the surface, but also in alternating between this polarization and this polarization. Okay, but now I want to look at a non-periodic structure, and my minimal loop is for such cubes going around an edge of the simple cubic lattice. Okay, so now we can consider different possible mutual orientations of these four cubes. Let's look, for instance, at this, and we're going to do that same procedure I showed before. We're going to draw yellow arrows for the displacement direction. If you press here in the, okay, so this is a blue cube, you press on it here, right, in the Z direction, then the X direction would go out and the Y direction would go in, as indicated by these yellow arrows here. And then this red block is oriented in the X direction. Therefore, if you press on it in the Z direction, the X direction goes out and the Y direction goes in, as shown here. And then you can continue that. And luckily here, you return to what you started from, so you're happy. Whereas if you take some other configuration of four cubes and try to do the same thing, you can verify that here you'll reach a conflict. Okay, and it's because of the exact same reason I was saying before, that here you'll have an odd number of spin flips around the loop. Therefore, this is frustrated. So now I won't show you all the details, but by some mapping to a spin model, we could identify that the number of compatible structures grows sub-extensively with system size, so it's huge. But as opposed to those these two-dimensional systems I showed you, well, actually, as opposed to the triangular system I showed you before, with that mapping to the Kagome here, the degeneracy grows exponentially with the surface area. So L is the linear dimension of the system, so the total volume is L cubed by the area is L squared, so it grows only exponentially with surface area, not with the volume. But still, it's a huge number of possible structures, which are typically non-periodic. But then we also show that we can use the fact that there is a single floppy mode in the system, and that floppy mode could have a very complicated texture in order to design the texture of that floppy mode. For instance, this is a 10 by 10 by 10 metamaterial that we designed it such that its floppy mode would look like this. Okay, so this is what happens if you press in one direction, and now I'm going to rotate it, and we're now going to press with a different phase, and you just get this alternating checkerboard pattern, and in a moment you'll see that when you rotate it again, you'll again see that the texture that we designed this metamaterial to have, and again, you see the scale bar by the fingers of my colleague. Okay, so you can design it to have any texture you want. Not only that you can design to get any texture you want when you press on it, the opposite is also true. If you press on it, say from this direction, with the texture that it was designed for, it responds more softly than if you press on it with the wrong texture. Okay, so this is just some neat application that maybe you can think of coming out of these combinatorial metamaterials. So now I'll briefly show you how we can use this formalism that we developed in 2D of these ferromagnetic and antiferromagnetic interactions in order to describe defects also in that three-dimensional system that at least we weren't able to see in our minds how do defects behave in that system. And again, using this mapping, we can do that, and I'll show that in a moment. So now, similarly to what we have here, I'm now going to look at these displacement arrows, and look, as I go around the edge in the lattice, the displacements on two adjacent faces could either both try to rotate in the same direction around that edge, or they can want to rotate in opposite directions. And that will define ferromagnetic and antiferromagnetic interactions in this octahedron shown here. Okay, and you can see that there are there's one plane in which you have all these endoferromagnetic interactions, so we're going to denote the orientation of this cube instead of by just this single red line here in 2D, we're going to denote it by this two perpendicular red lines here in 3D. And now, similarly to what we did before in 2D, we're now going to consider this minimal loop made out of 4 neighboring cubes and test whether you have an even or an odd number of antiferromagnetic interactions or spin flips as you go around this loop. And also here, there are only 6 possible neutral configurations up to rotations and inversions. And it turns out that these 4 configurations shown here on the left, in which you have an even number of antiferromagnetic bonds, are all mechanically compatible. And these 2 configurations shown on the right, in which you have either 3 or 1 antiferromagnetic interactions, namely an odd number, are geometrically frustrated. You cannot satisfy or assign displacement vectors simultaneously to all of the faces as you go around such a loop. And if you now look at these red lines, note that here I have 0, here I have 2 red lines, here I have 2 red lines, here I have 4 red lines, an even number of red lines meeting at the central vertex. Here I have an odd number, either 3 or 1. Right? So again, that's parity that we had before. But now we can use these defects in order to guide stress in the system. So this is that honeycomb lattice I showed you before and I'm not showing you the orientations of all the pieces there. I'm just marking the topological defect that I seeded in here in the middle. So these 2 images are of the exact same metamaterial, exact same structure, and we're pressing on it with slightly different textures on the left and on the right. And I'm causing stress to concentrate by that way either above the defect or below the defect. Right? So this is again related to the fact that as you go around and perform an entire loop around the defect, you have something odd, and therefore you need to have a conflict somewhere. You need to have some, if you want, you can think of this as some cut, I know, in some complex plane, and that cut has to go somewhere. It could, and you can direct by very small manipulation whether it would go downwards or upwards. If you now have 2 such topological defects, you need to have some line going between them, and this line could either go between them or it could go from each one of them to the boundary. And by that, by very small changes in the boundary conditions, you can cause stress to be concentrated either in this region between the 2 defects, or you can leave the region between these 2 defects relaxed and unstressed and have all the stress or energy concentrate outside. Okay, and also this, could be useful for various things. If you want to build a mechanical system, it's not direct which regions would deform and which would not. And now we can use this same formalism that I briefly showed you in order to go to 3D. So we can now take that 3D mechanical metamaterial that I showed you a moment ago and use those exact same notions in order to construct topological defects. Now, the defects are not point defects, but they're line defects that cannot terminate. So they need to go all the way to the boundary of the system. So this is a defect line here, and you can steer stress in the same way to go on one side of the defect or the other. In 3D, you can also twist that stress pattern. You have an additional dimension there, but you can also close a loop of that defect line. You don't necessarily need to go to the boundary. And then once you do that, like what we had in 2D, with 2 defects and guiding stress in the region between them or in the region outside them, also here you can guide stress to go through this window or to avoid this window and go around it. So to sum up, what I told you about is combinatorial mechanical metamaterials. So we're thinking of mechanical structures. Again, here all of our demonstrations are for practical reasons on the scale of our fingers so that we can play with them. But today, commercial 3D printing technologies allow you to build things that are much smaller than your fingers if you really want. And obviously, you can also build things that are much bigger. This concept that we're introducing is combinatorial metamaterials, in which, because we build these metamaterials and we need to prepare a file to send it to the 3D printer, we can prepare that file with any structure we want. We do not need to restrict ourselves to periodic structures. So coming from condensed matter physics, people typically think of periodic structures because in nature, when you have, you have a crystal, it has a periodic structure in them just because it's self-assembled to form that. But if now your structure is formed not by self-assembly, but by human design, you're not restricted to periodic structures and you can construct any geometry you want. And again, I think that the simplest thing for us to theoretically analyze was to take lattice-based systems in which we have some underlying periodic structure, but with some discrete degree of freedom, which in this case was the orientation of each repeating unit cell. And then just by these combinatoric options of what's the orientation of each repeating unit cell in the lattice, you can get really nice things like these topological defects. You can use that for stress steering. And another thing, which maybe I'll very, very quickly flash, or do I have a few more minutes? How are we with time? Or?
Yeah.
Okay, so another thing that we can do with these metamaterials, and maybe I'll skip this, is get sequence-dependent responses. Okay, so I'll just very briefly show you another project with, again, different lattice symmetry inspired by artificial spin ice. So this is some, this is called the snub tiling of squares and triangles in the lattice. It's the dual of the Cairo tiling, if anyone ever heard about these things. So the streets in Cairo are said, Cairo in Egypt are said to be tiled with these pentagons, and you get structures similar to actually the dual of this. But this specific structure was inspired by artificial spin ice, in which there is frustration by design, and also here we designed this structure to be frustrated, and now this frustration comes from geometric frustration and not by having a non-periodic structure in which we orient each unit cell separately. So here in this vertex, this 5-coordinate vertex, and where 3 triangles and 2 squares meet, if you go around it, there's no way to simultaneously satisfy all of these pieces. There's some frustration here, and this causes this metamaterial to always be in some disordered configuration in which no one is satisfied. Okay, and somewhere there is some contradiction, or you pay some energetic penalty. And now, a nice feature about this metamaterial is, as I said before, is that its mechanical response is non-abelian. It depends on the sequence of the operations that you perform on it. So I'm now going to take this metamaterial, grab these 4 squares in it, and externally manipulate them with my student's hand. I'm going to take these 4 squares and perform 2 different experiments, one in which we're going to flip them 1, 2, 3, 4 in the clockwise direction, and another in which we're going to perform the exact same operations, but now in the opposite order, 4, 3, 2, 1. And it turns out that when you perform the exact same operations, but in different sequence, on the same initial condition, you get slightly different final states. Okay, so by eye, maybe it's a bit hard to see the difference in these final states, so I'll highlight the direction of these beams here. You can see that, for instance, this beam here is bent upwards in the initial condition. In the final condition after this clockwise experiment, it's bent up, whereas in the final condition after this counterclockwise experiment, it's bent down. Okay, and I've just highlighted with color the differences between the 2 final states that you reach by the different sequences. Experiment, so this is the initial condition. We now duplicate the system, repeat the experiment twice with 2 different initial conditions, and now you'll see my student's finger manipulating the exact same 4 squares, but in 2 different sequences, 1, 2, 3, 4, or 4, 3, 2, 1. And eventually, after flipping all these, or performing all these 4 operations, the system ends. Sorry. I think I'll start with this. Thank you.
Thank you very much for very interesting talks. So we have. Sorry, yeah, we'll just get you here.
Oh no.
Thank you very much. It's very, very interesting. And your system, it is possible to apply the real material science on this. For material science, for instance, magnetic materials, polymer material, or polymer science, and some real material. So, possible to apply? Do you have an idea?
Okay, so I think there is, at the intellectual level, I think there are applications in both directions. I think that certainly we are, learning from what people do and know in material science for real materials that are made from atoms and molecules or polymers. We're using that knowledge and using all kinds of insights and techniques theoretically in order to analyze and explore these artificial mechanical metamaterials. The other direction is a bit harder because much of what I'm showing you here relies on my ability to sketch some geometry on the board and then send it to my colleague and have him 3D print it and fabricate a metamaterial for any crazy geometry that we'll think about. And in real materials, you cannot, tell each molecule where to be and whom to bind to. But I think, or I want to hope that there would be also a return transfer of knowledge and information from metamaterials to real materials. Because I'll give an example. In magnetic systems, and specifically, again, it's artificial spin ice, but still, these are magnetic structures at the nanoscale. I think there, gradually, we are managing to import concepts and ideas from these macroscopic elastic metamaterials to those magnetic systems. But I mean, we are limited.
That is, if analyze the spin glass system with the articular interaction, which is maybe possible to some more smart analysis for spin glass. Or some other magnetic material possible to apply feature. And then, did you try the gyroid structure? Gyroid structure is isotropic structure.
Okay. No,
It's a very special structure.
Mm-hmm. No, so that could be really interesting because we have, again, I didn't get into everything here in the seminar, but we also have many thoughts about chiral structures and the role of chirality. So
gyroid structure is one of the chiral.
Yeah, no, it would be very interesting and by that yet. Again, in other contexts, we have many chiral objects and phenomena. Maybe I'll just flash. So this is again another project in which we're looking at a simple triangular lattice, which is not chiral, but when you press on it, there's some spontaneous symmetry breaking, and locally, let's maybe start from the theoretical drawings. Locally, the system would choose to rotate in one of two possible orientations, and experimentally we also see that again it's still hard to follow identify the bending of these elastic beams experiment that is rotating in one direction here and in the opposite direction here. So we have been looking a bit at spontaneous symmetry breaking, but it could be also interesting to look at structures which are inherent in chiral.
Very insightful.
Thank you.
I have a follow-up remark, kind of. I recall we had a presentation by our PI, Hiroshi Sato, right? So when I think first part of his presentation, which you haven't seen, but it was actually about porous materials, right? That were real, kind of molecular material synthesized bottom up, and I can imagine that with proper, with the right design, some of the stuff could be repeated in this type of materials.
I mean, also the topics for DNA origami. The problems, but also they are floppy to the DNA other the third dimension.
Yeah.
But there may be ways to get reinforced structure, but I think that. So I mean, two questions. One is just one because how did this so you showed the defect groups. So when you principle design, how did defect into this structure?
Okay, so this is, I think, where my discussions with Ivan started. What is it? Like 3 years ago. And to the best of my understanding, with this specific unit cell design, we are limited with our ability to take these defect lines and do any topologically possible structure, like knots or linking to such groups. We tried looking at that and we failed, and now I also had many discussions on that with Tamash during the last few days. I'm not sure I have a rigorous proof that it is not possible, but I somehow have the feeling that this system is limited and cannot do that. But I think that working together, we could maybe think of maybe a slightly different unit cell design and local rules that would enable to have knotted structures for the decent lines.
So everything that you design right now is it and you design or is it by imagination, or do you solve an inverse design problem? For example, you by a sort of threshold with 3D structures when you create different phases and say, oh, you can do it for the shows a smiling face and so on.
No. That is like there we theoretically understand, like if we have a procedure that if you tell me what pattern you want, I can systematically construct a metamaterial by a set of rules that would give them. There's no that's again for each one of the different unit cell designs that I showed you, we fully understand the metamaterial that we can form from it, and for instance, things like give me draw me a smiley or whatever. These are things that we that have full theoretical understanding. What I think it does rely on a bit of intuition and trial and error is considering different unit cell designs. I showed you the triangular, the honeycomb, the 3D cubic, also some other things here that I can show you that the chiral tiling thing, but that is a bit more tricky, and there I think often we do search for certain functionality and then we can deduce what should be the building blocks that will give you that, but there is also a bit of intuition and trial and error there. It's not like we don't have a description that we can sell or publish the rules and you just follow the rules and then what they want. There is intuition.
And just maybe the silly question, but I'm just curious about the stability of the frustrated and non-frustrated structures. Of course, it's macroscopic. Maybe not certain. There's no way to accurately avoid stability, but you showed us that the big cartoon there. One is a frustrated, the other is a not frustrated. Once you push that to the structures, then which one is the more strained? Or maybe the deformation energies, which which structure, frustrated, not frustrated?
No, okay. So typically frustrated structures would be more stressed,
Really? Okay.
and non-frustrated structures would be more strained. Okay, so in the non-frustrated structure, these images, but in a non-frustrated structure, you can deform each one of the building blocks to its sloppy mode or its soft mode. So you can have a large amplitude, large displacement, but with hardly any stress. Whereas in a frustrated structure, you cannot deform without an energetic penalty or having stress, and therefore you would have stress and the displacement would be lower.
Yeah, if I could make that kind of a triangular structure, which have some asymmetric isotropic structures. Of course, the molecules you can just manipulate directly, but it's putting some certain solutions that you can make this some directional assemblies. And if you, of course, the molecules are maybe moving around in the solutions, but probably not organized. Appreciate that. Maybe that force, I think that's all determine the order of molecules upon the certain direction of the force. Yeah, if the difference is significant, I can do that. But and what about? Can you quantify the difference between the frustrated and frustrated structures?
I think that would depend on the physical details of the actual system.
Yeah, just put
that you have in mind, because
push the 100% energy put on that's the top place. Deformations require the energy difference is 10%, 20%.
no, I understand your question, but I think the answer depends on the physical realization. So again, most of what I showed you before is like scale independent, right? It's only about geometry and combinatorials. But then if you now want to take the next step and look at an actual system, like what you're suggesting, then you do need to take into account the physical considerations of the microscopic structure and interactions, etc., in order to get these quantitative.
Yeah, your talk is pretty inspiring for me because I'm a molecular chemist, but triangular structure can be synthesized by molecules. But you put this 3 pillars, one of them are just a little more flexible, softer unit you can put. Then that structure become anisotropic.
Okay.
And that's if your picture realizing the molecular assemblies, that might be a new technology to create the ordered structure.
No, I agree, and also another thing in that context is that I've repeated the fact that at least what we've done so far, and the experiments that we've been involved in, was 3D printing macroscopic structures in which you already design everything on paper before you print it. But maybe with self-assembly, and I think that follows also comment on DNA origami, if you have anisotropic units and they have specific binding properties such that we always want to bind according to specific rules, then maybe you cannot by hand orient each piece, but maybe you could cause the entire structure to find on its own a configuration that satisfies all of these matching rules, and that structure would not necessarily be periodic. It could satisfy these rules in many different ways. That could be really interesting. But again, there are, I think, there's further work there on things that are beyond my expertise. How to engineer these molecules in order to get specific binding, and also have to design the geometry or symmetries of the molecules such that they can self-assemble together.
I know we are a different world in terms of size. Okay, thank you. So I would ask so defect effect on the stress distribution you showed. So that in the two-dimensional the materials you showed just a point defect, so the distributed have changed. But in the case of three-dimensional material, you have to use the line or the square lines or something. So what happened in the point defect in the three-dimensional materials?
So the answer is very, very simple. For this system, you cannot have a point defect. So there are topological reasons that the line cannot terminate.
Thinking of just so stacking of the two-dimensional layers,
Yes.
so we can put in the defect in some part in the two-dimensional slices. So that in that case, so what happens then?
Yeah, but you can do that only if the slices are decoupled. So if indeed you have decoupled to these slices, then yes, you could in one of the slices put a point.
So no
defect.
interactions there over the layers.
But once you have interaction between the layers, at least in the context of what we've studied so far, you cannot have point defect. So always lines that cannot terminate in the bulk. They can terminate only on the boundaries.
Okay.
So that's why we don't have.
So the other question is, because you may be familiar with the kind of things, but so usually in the life sciences, so we sometimes use the vertex model to describe as an organ, like skin surface or something. So in that case, say as far as I see, my colleague has been working on the vertex model to represent so your organs like skin or some other organs in the biology. But so they don't have any anisotropic so deformation property of each triangles.
Right.
So so your presentation is very inspiring. Sometimes it's when we working on the deformation of our skin surface or the cell surface shape or something. In that case, the kind of periodical anisotropic unit assemblies that they may systematically change the long distance so shape deformation that happens usually in the biology systems. But my colleague usually use the very peculiar parameters putting on to reproduce the experimentally observed shape deformations. I think always the kind of artificial parameter introduction is so it's a kind of nonsense because just reproduce the experimental data, so nothing linked to the physical basics. So I think that kind of anisotropic unit involvement should be more the realistic modeling to reproduce experimental deformation systems. So have you ever tried the kind of things in your collaboration?
It could be very interesting. I know of vertex models for biological tissues. I haven't tried anything in that direction. I have some other work on mechanics of biological tissues, which is disconnected from all this. Also, there we didn't, I think, look at this confluent situation in which you have many cells in contact and then introduce anisotropy. There we did look at a bit of, I think, anisotropy of the actually microscopic structure of the extracellular matrix and how that becomes anisotropic to the mechanical activity of the cells. But it could be interesting also to look at what you suggest, the vertex model with anisotropic cells. I didn't do it.
Thank you.